Yes. It's all the Btech BW students. First, we'll take here the topic. So we have done with the working principle of transformer, EMF equation of transformer, E is equal to 4.44 F phi into N. Any problem on EMF equation, it will be direct substitution. We'll see those problems also. But let us move into the core topic of the transformer. So transformer on no load and transformer with load. So first we'll discuss clearly what is the transformer operation under no load condition. That means if the load is not connected to the transformer, is any current is flowing through the transformer or not is the question. So always primary winding is connected to the supply and secondary winding is connected to the load. If the load is not connected, if the load is open, is any current flowing through the transformer? If it is flowing, what is the name of that current? What is the value? We should explain with the mathematical equations and vector diagram. So first imagine the load is removed. So circuit diagram you have to draw this one. So you might get the question, explain the operation of transformer on no load. So draw the same diagram, okay, and simple one line magnetic field you can show, not this many. So here positive and negative are indicating that direction of the current starts from the A, this upper point. So no need to show this positive and negative terminal here. Okay. Now, when the transformer is operating under no load condition, what happens? So current flowing through the transformer under no load is assumed as I0. Let us say current flowing through the primary winding of the transformer is I0. I0 is the no load current of the transformer, which is assumed to be divided into two components. One is IM, as whenever current flows through the transformer primary winding, magnetic field is created. So the current which is creating the magnetic field is represented by IM, and it is called as no load component of magnetic field current. So we'll see that one. So when under open, when secondary is not connected with the load, current flows, which creates the magnetic field. You can see your magnetic lines of force. So the current which is responsible to create the magnetic field is represented by IM. So it is in phase with the magnetic field. Depends on the magnetic field. So again we draw the schematic diagram here. Now, only for the equation, let us wait. This vector diagram we have to draw. So under no load condition, so why you are getting this diagram? Under no load condition of the secondary winding, current flows through the primary winding. That current is assumed is denoted as I0. I0 is again divided into, theoretically, into the current which creates the magnetic field and represented by I suffix N. On x-axis, we draw the magnetic field first. IM is in phase with magnetic field. Therefore, IM is also drawn in phase or in the vector of the magnetic field. Here, magnetic field phi should be there. The current which is responsible to create magnetic field is the magnetic component current. Is the magnetic component current. So remaining amount of current will create the loss I square into R, power loss. So the current which is responsible to create the power loss I square into R is represented by IW or IC. Heat component current or watt-full component current, because it is performing certain real work. So IC is equal to or IW equal to watt-full component or heat component of no load current, and Im is the magnetizing component of no load current. So Im and Ic are perpendicular to each other. Therefore, after drawing the Im, we initially draw the Ic. So again, I am just taking it back. So let us take this one. So when under no load condition, current flows through the primary winding. The current flowing through the primary winding under no load condition is assumed to be I0, no load current of the transformer. I0 is divided into two different currents. One is IW or IC, which creates the power loss I square into R, whereas Im is the current which creates the magnetic field. IW and Im both are perpendicular to each other. So we should explain with vector diagram. Simple vector diagram we have to show. So if you see the vector diagram, yes, Im and IW are perpendicular to each other. Okay. So according to parallelogram law of vectors, what is a method to find the resultant, as I0 is a vector combination of Im and IW or Ic. So start from Im vector, draw a vector parallel to IW. Start from IW or Ic vector, draw a vector parallel to Im. So from the origin, the point of intersection of these two vectors is I0. So IW is in phase with the voltage, whereas Im is in phase with the magnetic field. So this vector diagram we have to show first. You can see first here, yes, Im and IW both are perpendicular to each other. IW is in phase with voltage, that's why it is drawn along with the voltage vector, and Im is in phase with the magnetic field. It is represented along with the magnetic field. Here it should be the magnetic field. Both are perpendicular. So the resultant is I0. Okay. From this expression, we obtain the mathematical formula. What is the value of Im and I0? We'll discuss that mathematical formula later on. Now, let us take the next most important topic is AutoTransformer. AutoTransformer is a single winding transformer. What is the main advantage? Whenever the copper saving is the advantage here. So whenever the coefficient of coupling for transformer we have studied, we got the formula N2 by N1 equal to V2 by V1 equal to I1 by I2 is equal to K. Coefficient of coupling value is almost equal to 1. We can use the AutoTransformer. So AutoTransformer is a single winding transformer where primary winding and secondary winding both are interconnected to each other. We'll see this one. Let us take the circuit diagram here first. So what is the AutoTransformer is the question might expect in the examination. Let us discuss this one in detail. Let us see. So AutoTransformer is single winding transformer which has got a common point, common terminal point here, the C. So I1 is the current entering the primary winding and I2 is the current flowing through the load. So both the windings, a single winding transformer at its common point is separating the primary and secondary. This primary winding and secondary winding. So in AutoTransformer, both the windings are electrically connected. I1 and this is I2. If you apply the KCL, so this particular part is I1 minus I2, and this is N2 and this entire winding is N1. So what we have to explain? Yes, explain with the vector diagram. The same thing. So if you see, we know for a transformer, the output voltage by input voltage. What is output voltage here? V2. V2 by input side, or else if you see, this is the secondary winding and this is the primary winding. The secondary winding voltage by primary winding voltage. So V2 by your primary winding is the entire thing is V1. So this particular portion is V1 minus V2. So V2 by V1 minus V2. Output voltage by input voltage equal to output turns by input turns. So what is output turns? N2. Similarly, here the primary winding turns is N1 minus N2, as we are taking the off of this one. So just cross multiply, and this expression is quite useful. So whether it is a transformer or auto transformer, V2 by V1 equal to N2 by N1 equal to I1 by I2 equal to K. So whenever voltage increases, current decreases in a transformer. Auto transformer, when I have to use, so wherever the power requirement, if the coefficient of coupling value is equal to almost equal to 1, and the size of the auto transformer is very less, the losses also very less, or efficiency is high when compared with ordinary transformer. So copper saving is the advantage of the auto transformer. All the currents are primary and secondary currents. Let us move to the derivation of copper saving. So as I mentioned, after this one, V2 by V1 equal to I1 by I2. So this expression, input equal to output. Now, what is advantage here? Second, auto transfer connected magnetically as well as electrically. Power, yes. So power is transferred through magnetic field and power is transferred through conductors also. So power transferred conductively is what we are supposed to prove. Output power across secondary winding. Power formula is voltage into current. We can take apparent power inductively is equal to voltage into current. The primary value is I2 minus I1. After simplification, we are going to get into 1 minus K. So this expression, if at all the paper is stuck, we are going to expect this one. So auto transformer, power is transferred inductively as well as conductively. This expression can show. Similar to the transformer, we have step up and step down. What we have taken, only you can go with the step down. That's enough. This only one diagram, no need to get confused here. Simple diagram. You'll see the next operation is transformer on load, that particular operation.